Hi, this is Dr. Staley. Today we're going to be talking about how to measure the nickel 2 content of a solution using the Beer's Law. So Beer's Law has to do with the absorption of light moving through some sort of medium, such as, a solution. The basic setup of the experiment is that you have a light source, you have your sample, and you shine light through your sample at a certain wavelength. You do one wavelength at a time and measure it at the end. And some light goes in, some light comes out, and the light that comes out gets to the detector. Now, the light that goes in has a certain intensity. Intensity is measured in units of energy. The light that comes out has a new intensity, which is presumably lower than the light that went in. Now, if we assume for the moment that that the only difference between these two is light that's absorbed, that's not always the difference. Sometimes light is reflected, sometimes light is refracted, sometimes the light is scattered. But if we assume that that's the only difference between these two, then we can figure out what the difference is, and that is the absorbance. Except it's not the absorbance. Even though the difference in this light is light that was absorbed, this is not the definition of absorbance that we use. The definition of absorbance that we use is that the absorbance of something is equal to the standard logarithm of the light that went in divided by the light that came out, both measured in intensity. This might seem a little weird, but the reason that we do it is because of the Lambert-Beer Law, aka Beer's Law. See, with the Lambert-Beer Law, let me use another color here. With the Lambert-Beer Law, the absorbance is equal to epsilon times C times L, so this is absorbance, this is the path length, which is how much solution does it have to go through. It's the literal distance from here to here. How wide is your sample? This is the concentration of whatever is doing the absorbance, of whatever is doing the absorbing, and this one epsilon is a coefficient the absorption coefficient epsilon is different for each species of chemical and also for each wavelength. This basically just says what fraction of the light, this basically just says how good the species is at absorbing light at this particular wavelength, or at this particular frequency. This law, this part right here, concentration and path length, was figured out by Lambert. This combination here, epsilon and concentration, was figured out by Beer. That's why it's the Lambert-Beer Law. This relationship was figured out before we had a really accurate way of measuring the intensity of light, which is the reason why absorbance is defined this way rather than this way. But that's not the only reason why. I want to give another example that might sound like a bit of a tangent, but isn't really. So if you have two solutions of water, and one of them has acid of known concentration, and the other has acid of a concentration that you're testing, and you connect them with a salt bridge of some kind, so that the acid doesn't pass through, but the salt can. And then you connect them with electrodes, then what you find is that the voltage between these two electrodes turns out to be some constant times the standard logarithm of the concentration of the acid, or rather the concentration of the acid in this one, if this is a concentration that can vary. And A is usually negative, so I'll just put a negative right there. Now, this is the reason why when acidity is measured, it's almost never measured in terms of acid concentration. It's almost always measured in what we call pH units, which is equal to the negative standard logarithm of proton concentration, or proton activity, you could say either. So here we've got the same relationship as compared to here if we put this logarithm in place of A. The reason that I bring this up is because this is actually something that occurs over and over again. If you need to go from something that is what I consider easy to think about, such as the concentration of an absorbing species, to something that's easy to measure, such as the intensity of light, you often end up with an equation that involves a logarithm someplace. Similarly, if you need to go from something that's easy to think about, like the concentration of an acid, to something that's easy to measure, such as a voltage difference between two electrodes, you end up going through a logarithm someplace. Okay, so there's that. And as far as the logarithm is concerned, there's one more thing that we need to think about before we move on. That thing that we need to think about is the detector right here. So the detector is going to detect light, right? And it is going to have to subtract the light that's coming in from the initial intensity. It's going to have to subtract the light that's coming in from the initial intensity. Now, the way that this works in most actual devices is that there's a second light path where this comes over here, and it hits the detector in a different place, or hits a different detector. So this detector can actually measure both of these. But the thing is, what is that actual difference? Well, if the absorbance is equal to 0, then the percent of light that is absorbed is also equal to 0. But if the absorbance is equal to 1, then the percent of light absorbed is 90. If the absorbance is equal to 2, the percent of light absorbed is 99. If the absorbance is equal to 3, well then the percent of light absorbed is 99.9. So at some point, absorbance becomes very, very hard to measure. Now, for the device that we have in the lab, I am not very confident about trusting it very far beyond an absorbance of 3. There are some commercially available spectrophotometers with detectors that can measure absorbance up to 6 or sometimes 8. I saw one that's advertised as going up to 10 absorbance units for certain wavelengths. But this is something that we have to take into account, because once we get close to the limit of the detector, we start to not be able to trust the data that we get out of it. Because, if we go above the absorbance limit, then we don't know what the actual absorbance is, no, do we? So, that is that. Now, with this out of the way, and let's go ahead and get rid of this. How are we going to do the actual experiment? How are we going to do the actual experiment? Well, we could, hypothetically, look up the epsilon value at a particular wavelength, and we could look up the path length at a particular wavelength. That doesn't change with wavelength. We could look up the path length of our sample, and we could then use those plus the in addition to the absorbance to determine the concentration of our sample. So let's rearrange this. Epsilon L, and in place of C, I'm going to have nickel 2 plus in brackets. When something is in square brackets like this, that means that we're talking about a concentration. So, to get this by itself, we end up with nickel is equal to the absorbance divided by epsilon times L. There's a slight problem with looking this up, and that problem is that you get much more accurate data if you just calculate it out for your own sample. So instead of looking this up, what we can do is we can do some standard, we can make a calibration curve which will tell us what this number actually is. So we know that the path length, in our cases we're using cuvettes. Cuvettes that always have a path length of 1 centimeter. The epsilon value we can figure out, and A is something we're going to measure directly. So Step number one, or I should say part number one, we're going to make standards. So standard, get rid of there, we'll get rid of that. Solutions of known nickel concentration Step 2, we're going to take a spectrum of one of those standards. Now, a spectrum means that we look at all of the wavelengths. We don't need to look at the spectrum for all of them. We only need to look at the spectrum for one, because what we're looking for is that we need to determine the highest absorbance. Hypothetically, we could pick any absorbance in the spectrum, but usually you want the strongest absorbance because that will give you the most accurate data. That will give you the most accurate information. Then after that, we want to measure the absorbance of all the standards we want to measure the absorbance of all the standards so that we can plot them. So this Beer's law, if it indeed holds, and it does, should give us, we plot absorbance here versus concentration of our standard, that should give us a fairly straight line. Actually, hypothetically, it should give us a perfectly straight line. Then finally, step 4, we want to measure the absorbance of our nickel salt at a known dilution. Once we have that data, we can put the absorbance on this graph, and because we're measuring nickel 2+ the whole time, that wherever that ends up, let's say hypothetically it ends up here, the absorbance for the salt is right there. What we would do is we'd go across here, we'd say, okay, so this is where we start with our absorbance here, and then we go all the way across. We say, okay, this is where those two lines intersect, where our salt absorbance and our calibration curve intersect. So therefore, the vertical axis, this right here, that is our nickel concentration. That right there is our nickel concentration in our salt. Okay, so far so good. Sorry, I keep forgetting you can't hear me. That they can't respond to me. Okay, fair enough. So now that we have this, let's talk about some complications that could take place. All right, complication number one. Other stuff absorbs. Epsilon doesn't often go down to zero, all the way to zero. It does sometimes, but not always. So because of that, we need to take into account that other things in the solution can also absorb light. So what we do for that is we take a background. That is, we measure the absorbance of a solution that has all of the same stuff in it that our test solution does and all the same stuff in it that our calibration solution does, except it doesn't have any nickel. Now, because our nickel salt uses sulfate as a counterion, we are going to be dissolving it in sulfuric acid so that the only ions that are there are also sulfate, which means that the background will be taken with a sulfuric acid solution. And because we're using a large excess of sulfuric acid to make the standards and also to make the salts, the test salt solution over here, because we're using a large excess of sulfuric acid in order to do that, the sulfate concentration is going to be the same in all of these cases. The second possibility for things that can go wrong is stray light or reflected or scattered light. The detector, so this whole experiment assumes that the only difference between the intensity of light going into the sample and the intensity of light coming out of the sample is the light that's absorbed. It also assumes that all of the light hitting the detector is light that has gone through the sample. This is not necessarily always the case. If, for example, the spectrometer is open to the lab and the lights are on in the lab, you could have stray light hitting the detector from a different angle. Now, the detector is stupid. It doesn't know which light came from the light source and which light came from the outside, which is why it's very important to always close the lid before running any of the scans. So for that, it's very important to close the lid. In addition to this, there's a possibility that, now what about reflected and scattered light? Well, some fraction of light reflects off of a surface once it goes through from one medium to another medium. And if that surface is maybe opaque or not completely transparent, or if it is irregularly shaped, some of it might actually be scattered in many different directions. So what we do to account for that is that we don't worry about it. No, I'm kidding. What we do is we make sure to wipe down the cuvette before each run. So before each measurement. What this does is because everything on the inside of the cuvette is the same between the background and the test solutions, except for the nickel concentration, because everything is the same, the only differences between the background reflectance and scattering and the test reflectance and scattering is something that could be on the outside of the cuvette. So by wiping the outside of the cuvette down before each measurement, we can make sure that the amount of light that's either reflected or scattered by the cuvette is the same between the background and the test solutions. So that way, it doesn't matter that some of it is reflected, some of it is scattered. All we're looking for is the difference. So there is, now that I think about it, one additional consideration. Let's just erase this here. Draw the line a little bit down here, a little further. Three. And that last consideration is that we need the concentrations to be concentrations that we know. And what I mean by this is we need to know that when we put a standard solution into the cuvette, that the concentration of that solution is exactly what we think it is. And that when we put the test solution into the cuvette, we know exactly how much the salt was diluted by. So what we need to do in order to ensure this is we need to rinse the cuvette with the new solution. We need to rinse it with the new solution before we actually put the sample in that we want to take the measurement of. So if we go from the blank solution to one of the standards, step one is to put some of that standard solution into the cuvette, shake it around, and then dump it out. because any droplets of water that are left in the cuvette after the blank are going to have the blank solution. So if we put our standard in after that, then it's going to be diluted by however much blank solution was left over. By rinsing the cuvettes and then tossing them, and then adding the solution back again, we can make sure that any droplets that are left over have the same concentration, or at least close to the concentration of nickel as what we think they have, and therefore they don't dilute it. So that is what we're going to do for the in order to measure the concentration of nickel in our salts. And yeah, so yeah, I hope that you all are safe. I hope that you all are healthy, and let's get to it.